is like apparently my fucking issue. And Bean Brothers is very good apparently.
Yeah, Bean Brothers is very, coffee is very strong. Yeah, very bitter. Very acidic.
Please, all right.
Hereby, I open the academic ceremony in which Andrei Utina will defend his academic thesis titled Instrumentation and Characterization Techniques for Advanced Gravitational-Wave Observatories. Dear candidate, may I invite you to present a summary of your study and the conclusions of your thesis?
Yes, thank you. Dear Prorector, dear members of the Defense Committee, dear supervisors, and dear friends in the audience. First of all, thank you all for being here. In the next 15 minutes, I would like to give you a presentation about my thesis with the title Instrumentation and Characterization Techniques for Advanced Gravitational Wave Observatories. The strategy for the talk would be to give you introduction at the beginning and then directly transition to the research highlights. So gravitational waves are ripples in the fabric of space-time, predicted by Einstein in the theory of general relativity. They are produced by very heavy masses in the universe rapidly accelerating. There is an entire spectrum of gravitational waves, and the sources can range from extreme low frequency sources produced by, for example, the Big Bang itself. And if you go higher and higher in frequency, you can have sources in this range of 100 to 1,000 hertz, and these are produced by compact binaries in our galaxy and beyond. These compact binaries they can be binary neutron stars or binary black holes colliding and producing gravitational waves. The higher frequency sources depicted here in this violet shaded box, these are the focus of my thesis. And they are detected usually by ground-based laser interferometers. The way ground-based laser interferometers work is by the simple principle of interference. Suppose you have a beam depicted in this figure here. It shines at the beam splitter and you split it into two orthogonal arms. Then you can tune the interferometer in such a way that when the beam recombines, the two beams in the two arms are out of phase. So it's a destructive interference. You have no signal at the output port. Now, if a gravitational wave hits this plane, because of the nature of the wave, it's quadrupole in nature, it stretches and squeezes the arms differentially, producing a differential response, and you might have some constructive interference at the beam splitter, which gives rise to some signal that we can measure. This is the simple detection principle. Now, just to give you a little hint for what's coming, in reality, it's a bit more complicated, and the interferometers are formed by a lot of cavities that we need to control on resonance. You need to clean your input beam before sending it to the beam splitter, and you also need to clean the output of the beam. And either the arms of the interferometers are resonating Fabry-Perot cavities. To give you a sense of scale, suppose you have your 1 micrometer laser, your favorite laser in the lab. It's about 1 micrometer in size. Now, if you look at the diameter of an atom, it's about 10 to the minus 10 meter. If you look inside an atom, you have 10 to the minus 15 meter, the diameter of a proton. Now, what LIGO measures, which is the current detectors of gravitational waves, is a differential measurement of 10 to the minus 20 meter. Typically, we measure strain. So as I said, it's differential measurement over the arm length, and the arm lengths are of the order of the 4 kilometers. So this strain is about 10 to the minus 24. Now, in order to measure these extreme sensitivities, you have to understand all your noise sources in the detector. And there are a lot of noise sources that can mask and mimic the gravitational wave signal. In my thesis, I'm dealing more with the fundamental noise sources, and these arise from the physical effects on the test masses. There are two main types. There are displacement noises. Displacement noises are noises caused by stochastic displacement on the test masses themselves. And you have also noise in the laser field itself. These are called sensing noises. A good example of this is the gas noise. So we're operating these interferometers in vacuum, but you might still have residual particles in the gas, in the arms. And these gases, they produce displacement noise because they interact with the test masses, but also sensing noise because they interact directly with the laser field, producing fluctuations in the path length. Another source that is a bit relevant for my thesis is the seismic noise, which is, seismic noise is simply the coupling of the seismic activity of the ground to the test masses. And usually in gravitational wave observatories, we hang the masses on cascaded of pendulas. And you see here a little, on the left here, just a little depiction of these systems. We call these systems suspensions. So in my thesis, I was simulating all these fundamental noise sources for a gravitational wave detector. And to give you a sense of how they might look like in reality, you have here a plot on the right of it's a strain of the detector. This is the strain, the actual noise of the detector during the first measurement. So we measured the first gravitational wave on the 14th of September 2015. And you see here by the blue and the red curves, these are the two LIGO detectors that measure gravitational waves. And also you see the corresponding characteristic strains of this wave. And typically we see the visual picture here is the area under the curve between the characteristic strain and the noise gives you the signal to noise ratio. So improving these noise sources, reducing it will automatically improve the signal to noise ratio. So currently we're operating a network of gravitational wave detectors. These are just two examples. We have more interferometers. There are two main LIGO interferometers in the United States. We have one in Hanford, and the image here on the top is the one that is in Livingston. And we have the Virgo detector nearby Pisa in Italy. Since the first detection in 2015, we actually detected a lot of sources. And what you see here, this is what astrophysicists call the graveyard. This is how many detections we had up to only 03, which was around when pandemic kicked in. So all these blue dots here were binary systems, binary black holes detected by LIGO and Virgo. And all the orange points were the binary neutron stars, the neutron star systems. So you see that we filled in already a huge gap of knowledge, and we improved a lot the understanding about the universe. However, we want to go to the next generation of gravitational wave detectors. And Einstein telescope is such a detector. Now, we want to measure with these detectors hundreds of thousands of these sources per year, and even to tunnel to the very dark edges of the universe where we can potentially detect fascinating sources, such as the dark matter candidates. Einstein telescope achieves that with having at least 10 times better sensitivity broadband compared to the current detectors. And it does that by introducing, it's not simply an extrapolation of the current detectors, but it introduces also new technologies. And I will not mention all of them, but what's more relevant for my thesis is, for example, this xylophone detector technology, in which you combine a noise source of two detectors. One is tuned for low frequency, and one is tuned for higher frequency. Especially the low frequency detectors has to include a lot of new technologies. And just to mention, we have to use 1550 nanometer laser light instead of 1064 that the current detectors use. And also go to cryogenic interferometry to cool down the test masses to reduce the effect of the thermal noises. And now I would like to transition to my research highlights. We cannot simply go to, and this is the case in all the domains of physics. If you want to build large-scale facilities, you need to test all these critical technologies first. And ETpathfinder is such a test bed for the critical technologies for the new generation detectors. In my thesis, I would say as a main highlight was that I was developing parts of the ETpathfinder optical design and simulated the fundamental noise interactions and produced these noise curves, these noise budgets. So you see an actual picture of ETpathfinder here, which is, ETpathfinder is built by Maastricht University. So it's actually across the river in the DAP 30 building. You see the optical layout of ETpathfinder. So it's also L-shaped, but we have actually interferometers folded across arms. So on the horizontal axis, we have the 1550 nanometer 18 Kelvin ETpathfinder A interferometer. And on the vertical axis, by the red light, we have the ETpathfinder B, which is the interferometer running at 2090 nanometer and 123 Kelvin. You see here the noise budgets as well, and just maybe a big some highlight of what we achieved here is we were in fact in the target we're looking for at the beginning of the design of ETpathfinder was the displacement of the best detector, the one that is cooled down to 18 Kelvin, has to be around 10 to the minus 18 meter per root hertz at 10 hertz. And that's achieved there on the top plot. And it's also good to notice that we are limited, in fact, by the noises that are the most relevant for the new generation detectors. So we can test all these new technologies and see how these noises interact. As I said, we want to go to cryogenic, but it's important to go to cryogenic temperatures without introducing new noises or more noises to the system. And one of these noises is the cryogenic noise, that the seismic noise that can come from the cryogenic systems. So during my thesis, I was doing an experiment on a prototype suspension system that you see here. It contains an inverter pendula, this long leg. It has a suspended filter that suspends a cryogenic payload. And this payload, it was the first prototype actually for ETpathfinder. And the way noise is introduced into this system is it has two pathways. So you have seismic noise that comes from the ground via the suspension system and coupled to the test mass. But the fact that you're cooling down the test masses and you have to cool down in a fast enough time, you need to cool it conductively, it means that you interact with the test mass. So you have a shortcut from the cryogenic system to the test mass that can produce additional seismic noise. So in order to understand the impact of this noise, we need to measure and understand the impact of how the seismic system is coupled into the suspensions. And in this first prototype, it was coupled via these suspended rings that have the very soft conductive heat links in between. We call them jellyfish wires. So I had to do an experiment to test the vibrations between these two rings and test to see if my analytical model is correct, such that we can use it in ETpathfinder. And you see it here on this plot. This shows you the measurement by the black curve. The red points are also measured, but in a different way. And you see two types of simulation. One was an analytical simulation of two-wire geometries, and one was a finite element simulation. So it agreed well, but I still had to calibrate this. And this allowed me to extrapolate this noise to the full ETpathfinder, to integrate it in the full system. And you see this here. What you see here is by the thin gray line, this is the ETpathfinder curve. It's the one that it's running at 18 Kelvin. And below 1 order of magnitude, you have the requirement. And now at that time, I was calculating that we need around 20 heat links to cool this in a fast enough time. And you see if you double the number of heat links almost, if you go to 35, you're reaching already that threshold. So this study proposes a new method to characterize the noise induced by the cryogenic heat links, such that we can derive requirements for the stability of these cryogenic pathways. The next two chapters of my thesis deal with how to control these gravitational wave detectors. As I said, the detectors, they have a lot of optical cavities and they are strongly coupled. So before we actually detect gravitational waves, we need to control all these cavities. And I'm showing here only one, for example. This is called DARM, is the differential arm length. It has to do with the difference between the two lengths, the two long lengths of the interferometer. Now, once we control this interferometer, we lock it. We lock the interferometer. And we have to control it actually to bring it to the operating point in a sequence that we call lock acquisition sequence. So to give an example of how we might lock a cavity, you do that by modulating the carrier and producing sidebands. Now the carrier around the resonance is the phase is very sensitive, but the sideband, since you can modulate it in such a way that it's not resonant in the cavity, this phase is not that, it doesn't care about resonance. So you can produce a static phase reference to actually sense the length detuning. And this is the method that we actually do in the gravitational wave detectors. Now, what I was doing in my study, I was doing a survey of all these relevant sidebands for advanced Virgo detector during lock acquisition, on the lock acquisition sequence during O3. And this is an example. I was, on this plot here, I'm showing, for example, a 16.7 megahertz sideband. And I'm tracking the evolution. I'm extracting data, and I check my simulation against the data. And what you see here on this plot is on the x-axis, you have as the interferometer is being brought to lock to the operating point. So 0 means we're locked, we detect gravitational waves. And you see 20 locks, and you see the evolution of the sidebands. And this evolution against my simulation. So this was a good example. This was matching quite well. It was actually a Pearson coefficient with some biased data was around 0.86, I think. And we found a lot of good matching like this. And this analysis brings a new way of characterizing these sidebands, and it helped the commissioning team, the instrumental sensing and control commissioning team during O3 for advanced Virgo. The last part of my thesis deals with automatic pre-alignment of optical cavities, but the angular degrees of freedom. So as I said, we have the interferometer at its operating point. The light resonates in there, and what you have resonating is the fundamental mode, the Gaussian mode, the so-called transverse electromagnetic 0-0 mode that you see here on the first picture. Now, before actually achieving this, you can imagine the mirrors, since they are suspended on pedula, they are freely swinging. And we need to pre-control, pre-align the interferometer. So there are complicated methods to do that, and they have to bring new sidebands into the system. But what I thought is possible is to use a simply pattern recognition-based approach, and we can do that with machine learning. We can recognize these mode patterns, and we can turn them into error signals. So on a suspended cavity at NICEF, we extracted experimental images, and I trained the bidimensional convolutional network directly on these experimental images to recognize mode numbers. And based on these mode numbers, we could create error signals that can actually interfere with the control scripts and log the cavity on resonance. So an example we actually did is, this is experimental data in which you see an example of a very large higher order mode. The cavity was really swingy. And then with this method, sequentially, this cavity is being brought to the linear regime where we can actually lock it. This was my last slide. I would like to thank you all for listening. And right now, I would like to give my words back to the director.
Okay, thank you very much for your presentation. Before we proceed with the opposition, let me briefly introduce this committee to the audience. So on my opposite left, we have Professor Hield. Next to him is Dr. Steinlechner. These are the thesis supervisors. Then we have Professor Onderwater, Professor Merck. And on this side, we have Professor Freise, Dr. Steinlechner, and Dr. Danilishin, who is the secretary of the degree committee. Finally, my name is Duisman, and I'm representing our rector for this meeting. In the next 45 minutes, questions will be asked by the members of the assessment committee, and the opposition will now be opened by Professor Freise, who is a professor of gravitational wave science at the Department of Physics and Astronomy of VU Amsterdam. Professor Freise, the floor is yours.
Thank you. Yeah, dear candidate, before I start asking questions, let me first congratulate you and also your supervisors on a really nice piece of work. I mean, it's always enjoyable for us to be part of this procedure, but your thesis reminded me a little bit about why I like this field, because it's so diverse. We have the opportunity to work on different subtopics of physics or engineering, and you covered quite a lot of ground, from optics, seismic, the design studies, the experimental work, so that was very nice to read. Well done. I would like to ask some questions, and I will focus most of them on chapter 2 that you also shown in your talk, just because it resonates most with me. Could you start by looking at figure 2.7, where you show the powers that you measure in the interferometer over the lock steps? I have a few questions, but first, can you just tell me what is actually the goal? So if you look at the powers, what do you want to achieve? So what's the good state at the end?
Yes. Dear highly esteemed opponent, thank you very much for your kind words and your interesting question. Starting with this, this figure shows basically the DC powers evolution. Using finesse, I was trying to simulate this lock acquisition to see if the DC powers can really resemble what we expect during lock acquisition. So there are different phases, and I think some people have different ways of simulating this. You see I brought it into chunks, so the x-axis for me did not really matter. But what I wanted to focus here was the last part, the step 4, in which I was looking at, because my analysis extracts sidebands only at step 4. So that's when we bring from the 0.5 Michelson, we bring it to lock, and that's where the sidebands are extracted. So in that case, I was looking at the evolution of these amplitudes, and I was matching this with the expectation, because you see the x-axis on this plot, actually, on figure 2.9 or 2.8. the Mitch set point is different than what you expect. I think it should be 45. But I was matching these evolutions to what was expected in terms of the DC powers. When we bring the interferometer from mid-fringe to lock, there is an evolution of all these DC powers that people expected in Virgo. And I was trying to match that such that I'm in this position that I can actually simulate sidebands, and I am confident that they behave well.
So what is the key DC power that you want to achieve? I mean, we see here, what are the 5 traces? So what is the thing that you want to achieve? Just in words, for one of these signals.
Yeah, so in my analysis, the y-axis, the power is a bit, it doesn't really matter because I'm looking at the trend. So I was looking to have the field trend consistent to what was expected. So in terms of power here, when I'm simulating the sidebands, I had, of course, the difficulty there was calibrating this x-axis with what was expected. So there is actually this calibration, which, yeah, we can discuss later. There is.
Yeah, I think you misunderstand me. I really wanted to just have a very simple question why you say high power is good. Huh? Let me just ask my second one. It's, again, very simple. Huh? The green trace has a dip before you reach the end of step 4, and you describe it also what happens there. So why is that dip happening before you reach the final state? So green is the B4, the B2 PRC reflection. Yeah,
so I think there you're supposed to be critically coupled in the PRC. The PRC should be critically coupled, and the reflectivity of the PRC compared to the blue curve, so to what the arms transmit, should be 0 in that case. I think there is an equation that for critically coupled that should be 0. So they should come very close together if you look. One is rising, the transmission of the arms is rising, and that's dipping there. What I've seen also, a similar plot is they really touch a bit and they overlap, but it's never clear whether they should.
Yeah, correct. So but my question is also, I mean, apparently we are critically coupled when we are in the dip, as you described, but your end state, we are going into overcoupled. Why?
So you're going to overcouple because you want to gain light in the PRC. So that's an interesting question. So are you asking why at the locking we're actually overcoupled?
Yeah, is overcoupled better than critically coupled? That's my question to some extent.
Yeah, so at the critically coupled, I don't think it's in this case with the sidebands, they can be extracted across the entire evolution. But I think at the critically coupled, there was nothing peculiar with the sidebands. So in terms of the DC, yeah, I understand that difficulty there, but I'm not sure if this really influenced this.
No, okay. Yeah, so in fact, this was just a preparation for your actual work, which is looking at the sidebands. You showed one of the plots already in your talk. I would like to ask you a few questions about the, but maybe we'll pick the other one. If you can take 2.17, which is just the one that doesn't fit so well, but it's the same type of plot. So I understand roughly what you're doing, but I didn't understand exactly what you mean by the dots that you call calibrated data compared to the logs. Can you explain that again?
Yes. So calibrated data, as we bring the interferometer to its locking point, some of the sidebands were badly behaving, and they had to calibrate them a bit. They had to the modulation depth had to be decreased. So if we look at figure 2.14 on page 43, you see actually this, so only 6 megahertz, which 6 megahertz was the entire reason for this analysis, because during lock acquisition created a lot of problems. So the modulation depth, the amplitude of the sidebands were decreased just because it was not manageable to lock. They found a lot of noise during lock. Okay. So the calibrated data points are the ones that actually include this, effect. Because in my simulation, there was no modulation depth. So I had to match the data with simulation.
Okay, yeah, okay, I understand. Very good. And then I think you conclude what you see in the plots, then all in these in the table 2.3 with the Pearson correlation coefficients.
Yeah.
I found this very interesting, and to me it looks a little bit like if you defocus your eyes a little bit, then I thought, okay, it's a sensing matrix. Can you explain a little bit to me what's different between what you've done here and the sensing matrix? I mean, I can make a sensing matrix not exactly like this, but you would have sensing matrix. You had B1, B2, B4 and one thing, and rather than the frequencies, you would use the let's say which signal you want to control with that frequency, but then it might look very similar. So what's the difference between a sensing matrix for this particular setup and this table?
Yeah, so that's quite interesting. I've never thought about a sensing metric here. I would imagine you need a sensing metric for the entire operation. So here I'm looking at a small range on the local acquisition, but you need to control these degrees of freedom from the beginning. So the optical gains of these error signals have to be computed for the entire local acquisition. So I'm looking here at only one chunk, and I think for some of these high Pearson numbers, I think only a few during the local acquisition, only a small range of that process is relevant for the fitting.
But still, I mean, maybe correct me if I'm wrong, but if I understand this correctly, a high number means I get a sensible signal if I look at that port for this frequency, and a red number means I don't get a sensible signal if I'm looking in this port for that frequency. Isn't that also maybe a sensing matrix issue? Like if I get a high coefficient, that means I get a high signal. If I get a low coefficient, that means I get a low signal, maybe covered by noise, so it's not correlated anymore. So maybe if you make, which you haven't done, but if you would make a sensing matrix, might be the distribution of coefficients be similar?
I would expect so.
Yeah, well, I mean, I don't know. But
even though we have
somebody should try.
I'm expecting this, but we have it's still the simulation part that we interact with, which I think we don't really know if, because this was the point, can we really with a perfect interferometer match these evolutions? And I think, I'm not sure if this answers that.
No,
we still need to understand that, yeah.
Okay, I think I'm satisfied. Thank you.
Thank you.
Thank you very much. The opposition will now be continued by Professor Onderwater, who is a professor of experimental particle physics and director of the Maastricht Science Program at Maastricht University. And he's also the chair of the assessment committee. Professor Onderwater.
Thank you, meneer de Prorector. Dear candidate, I'd like to join my colleague in congratulating you on this nice thesis that you have produced. It was a pleasure to read it as a member of the assessment committee, and I also join him in complimenting you for the broad variety of different topics that you've managed to bring together, which shows that the field of gravitational wave detection is way broader than just general relativity. So congratulations on that. Still, some questions. I would like to discuss predominantly Chapter 5 with you, where you present your introductory efforts, perhaps I should say, on using molds as a tool to make an automatic alignment of the cavity. First, perhaps we have a brief look at equations. Let me see where I wrote that down. Equations 5.6 and 5.8, which you can find on page number 120. And there you describe the effect of a small shift, horizontal shift in X, or a small rotation along the y-axis here, I suppose, and the resulting effect on the mode pattern. Now, what you suggest here is that the mode pattern gets a mixture of what you call U1, all right, with an amplitude which is proportional to either the shift or the rotation. Do I interpret that correctly?
Dear highly esteemed opponent, first of all, thank you very much for your compliments and your very interesting question. I think the interpretation is correct, yes.
Okay, so this then, okay, thanks. So this suggests that if you want to measure this, well, let's say horizontal offset X, that you expect some sort of linear dependence on the admixture of this U1 mode in the total pattern. Is that a correct interpretation as well?
Yes.
Okay.
As far as I can see right now, that's the correct.
Okay. Yeah, because from very, very long ago, I remember my laser days when a typical laser, which is also sort of a cavity, simply would entertain one mode, and when there's a perturbation, it would hop from one mode to the other rather rapidly and would not show an admixture in the way that you suggest here with a small amplitude. Is that indeed what is happening? Do you get a mode hop, or do you get a small admixture of, for example, this TEM01 mode?
So, yeah, okay, I think now I understand.
Perhaps also
so in both questions we have the fundamental mode, and then you have some other component that it's linear to the first order mode in that case, U1. So this equation tells me that it's indeed not hopping, but it's somehow enforcing the fundamental mode to go to that.
Okay.
So you have a superposition.
So that this should give you some sensitivity to indeed this deviation in X. Do you have a goal there in what sort of a range of X's you're planning to measure? In other words, is an admixture of this TEM01 mold, is that enough? Or are you prepared to look for large shifts in X up to the point that you would have to include, say, a TEM05 mold or something like that?
So this analysis was only to motivate a bit the usage of the higher order modes. But I think the question is also relevant for my second chapter, where I actually looked at this error signal. And in that case, we had a fundamental mode in the presence of a higher order mode. And we tried to create an error signal to see if we can correct for this. Because in the current detectors, we don't correct for that. We correct for, we want to bring the cavity to some linear regime where we can actually form an error signal that is typically used. It's a very behaving error signal. It's called a PDH error signal. But you can create also with this some sort of, let's say, signal, some feedback signal that can create an offset, can give you an offset for actually detecting the length deviation from resonance, or the angle deviation from resonance in that case of a cavity. So the actual scale of that, it depends on your modulation frequency, of course. So I don't know, in my case, usually the higher the modulation frequency is worse because the linear regime is around 0, is quite steep, so you cannot really use that linear regime. So I cannot tell, maybe some, I don't know, if you want a number, a few megahertz.
Okay. I was just curious to see if this first order approximation, which is obviously where you start with, whether that is sufficient to reach the goals. And in general, I think gravitational wave detection strives for ridiculous precision everywhere, so I imagine that these X's are quite small. Okay, now then maybe on the practical part here, this is a mode pattern on the amplitude of your electromagnetic field. What you measure with your detector is actually an intensity profile. So at that point, you're going to square the amplitude. And if I do that, I find that the intensity profile should be a sum with an amplitude squared for the pure admixture mode, but it should also have a combination of the two. The interference, if you want, between the 0,0 and the 0,1 mode, which leads to its own pattern. Looking at what you trained your neural network with, it seems that you trained it with the pure modes only. How will that affect? Should you train your neural network also with interference patterns?
Yeah, so in fact there is some research with neural networks in which they try to do this decomposition of the amplitude and phase components. So in my case, I trained directly on the intensity images, these transverse modes. I think you gain some information, so you can improve if you use also the other component in training here. And what we propose that for this approach, we can use more other signals. So instead of I'm training directly on images, so it's a bidimensional training, it's just a pattern. But you could use also the error signals itself. You can create a multimodal approach in which you use different information that you have to actually learn the patterns. So you could also use that, yes.
Okay.
It can be an idea for future research.
Okay, nice.
Which we also propose.
And perhaps a last question, which is somewhat mathematical in nature. I see that you chose to decompose your beam pattern in terms of Hermite Gaussian modes, which in my recollection are modes which are best described in Cartesian coordinates, x and y. But I also assume that the setup of the Pathfinder is, again, ridiculously symmetric, so I expect more a circular or cylindrical symmetry. Is there a reason that you picked Hermite Gaussian modes rather than Laguerre Gaussian modes, which are best suited for cylindrical symmetry, or for that matter, even I think there are In's Gaussian modes which deal with elliptical symmetry?
Yes, so I think this has to do with where we look at symmetry, exactly. And I think for these resonant cavities, where we actually do these solutions, Hermite Gaussian solutions, or just the typical Gaussian beam, the symmetry should be on the transverse plane and not along the, yeah, so along, of course, we treat the Z component there. In this derivation, we treat it as constant, so we get rid of it to actually derive the Gaussian mode. But I'm not sure I'm going in the right direction.
I don't have a right direction. I'm just curious why you picked these modes, or whether there's something I did not understand just yet.
Yeah, it was pretty much standard to use this approach to derive the signals, to derive the modes of it. Right. Yeah.
In the end, each and every one of these sets of polynomials are complete sets, so you can use whatever you like. Of course, the question is, how do you get the easiest life possible? And then you pick the one that suits your purpose best. Okay, now looking at the time, I thank you for your thoughts and your insights, and I give the word back to the prorector.
Thank you. The opposition will now be continued by Professor Merck, who is a professor of collider physics at the Department of Gravitational Waves and Fundamental Physics at Maastricht University.
Thank you, Mr. Prorector. Dear candidate, also from me the compliments with this beautiful, lively manuscript. Lively, I should say, but I mean also a lot of topics being addressed. And I think even as an outsider in this field, which I clearly am, I think I can recognize all the wealth of the studies that you've done. It was mentioned already before, on all these vibrational noise sources for Virgo and also the next generation experiments. While I was reading through it, then you read through the thesis, and then full of respect of all these details, and at the end, I meet the prepositions. Propositions, and then at the end, the very last one of it, I thought, hey, that's interesting. So may I ask one of your paranyms to read that proposition to the audience? Yes. Number 8.
Proposition 8, directly probing the early stages of the universe prior to the recombination epoch is only possible by detecting gravitational waves.
Thank you. Now my question is on this topic, and first of all I think yes, of course, that's great. But then I thought, there's also these particles, neutrinos.
True.
How is that? Is this in agreement with your statement? Are they not included, or what are you referring to with the statement?
Dear highly esteemed opponent, thank you very much for your nice words. And the very interesting question that I actually expected. I looked over this and it didn't make sense for me. So what I had in mind initially when I had the proposition written was during the inflationary phases of the universe, there are a lot of mechanisms producing gravitational waves. And I was looking at the literature over time, and first of all, these are backgrounds of noises, and the literature improved a bit on how we disentangle between different backgrounds. And also, of course, the literature of these sources is very rich. So my thought process there was like, for these very small scales, like 10 to the minus 30 seconds, 10 to the minus 20 seconds, this is the only kind of solution we have to look back at the universe with gravitational waves. But then the mistake there was to put the recombination epoch as a time frame, and I realized this is the relic neutrinos. They are about 1 second after the Big Bang. You have them in there. So the fact that I put that time scale there was a bit wrong.
Fully understood. Thank you very much. It's very clear to me. Yeah. And then let me go more into the technical details on your noise studies. I was intrigued by your studies on vibrations, which are summarized at pages 92, 93, 94, and in particular these figures 4.2 to 4.5 even. And I realized when you have these cold fingers, you have these delicate contacts, which now are a source of noise, if I understand correctly. And then I look at I think I got triggered by figure 4.3 when you're doing this measurement to analyze his behavior. And then I thought, aren't you also introducing noise when you do the measurements? So what are you measuring? Is that the real noise, or is it also a measurement component of yourself being affected? It's a very generic question I had when I was looking at this plot.
Yes, so in this case, you see the pendulum in figure 4.3 on page 93. So you see the actual measurement setup there.
Yeah.
So there are both of this, the red ring and the ring above, they are 3-filar pendula. So they hang on 3 wires already. And they are pretty much in their equilibrium state. So on this system, I'm introducing accelerometers, which are these black tubes that you see attached there. And then I'm resonating the system. I'm introducing noise to actually measure the transfer function.
Okay.
So before starting the measurement, of course, I'm calculating the weight of all this. So we're putting accelerometers. We're imbalancing a bit the pendula. It has additional weight. So I have to take into account all these things. And when you perform the measurement, yeah, it does.
So for example, this channel 1 and channel 2, which are connected to your signal analyzer, they don't introduce noise?
Of course, they will introduce the noise, like the noise floor, the electronic noise of the instrument. When you do the additional, the transfer function is channel 2 over channel 1 in this case. And you have the noise there. There will be noise.
Okay.
But the fact that we're measuring, in terms of dynamics, for the heat links, it does not introduce additional noise. So in terms of just the mechanical dynamics.
Okay, thank you. Now I understand that you have all this wealth of studies, and suppose now we're going to commission the next generation device. And maybe you want to test it also in the ETpathfinder, what you're doing there. Now I read a little bit on, you can control these noise measurements with a null stream if you have a triangular setup. You know about this. How can you test this with ETpathfinder? Because as I clearly see, that's not a triangular setup. Is there a way to test the commissioning of a triangular setup even with ETpathfinder? Maybe that's my question.
So the short answer would be, I don't see that possible. But what I see possible would be to test the actual interference null condition. So each interferometer has a null. You work under the null hypothesis that at the beam splitter, if everything is perfectly out of phase, you have no signal coming. But of course, there will be a lot of signals coming. And you can test this. That's the purpose. The entire business of adding noises, adding different technologies would be to see that this displacement curve, is it actually there? Because otherwise, you have you don't reach this null condition. So you can reach null conditions also for a simple L.
Okay.
You don't need the entire triangle. Okay. Triangle is relevant only for sources.
Well, okay, I think you answered my question. I think I'm happy with that. And I'm looking at the pro-rector. If there's room for another short question?
Yes, please go ahead.
Okay. Then I'd like to make it more general again. My question is, you studied a lot of this noise sources for laser setups, for very high precision. And then you went to ASML. You do lithography. Also with laser setups, also with incredible precision that you guys have to work with there. Is there any cross-learning experience that you have from there to here, yes, or the other way around? Maybe I'm also asking, is there some collaboration possible to understand certain special effects, or is that thinking too far? What was your opinion on that?
That's interesting, yeah, because I have this ASML experts here on the front row. So what I see right now most obvious is a lot of expertise from that side that is relevant for gravitational waves. But on the other side, what I'm doing, it's not really, with all these noises and this precision, it's not really applied daily to my learning.
So the precision is too much that you have in gravitational waves is not comparable to the sub-micron precision that you have in your lithography.
Well, it depends where I'm working on the source on the UV machine. So there, it's not much controlling. Okay. It's more like understanding what light does, interacting with different surfaces.
Okay.
But I think in terms of precision, at least what just seeing talks and so on, I think they're super advanced in the feedback control, and the interferometry that they do, they have way more degrees of freedom that the gravitational wave has. So there is a lot to learn if you talk to a lot of people in different groups.
Okay.
So there's a lot of overlap. But in overlap from that field to gravitational waves, it's a lot with what I'm doing right now, especially the ray tracing part and so on.
Thank you. We should certainly keep that in mind. Thank you very much. And I return the word to the prorector.
Thank you very much. We now go to Dr. Steinlechner, who is an associate professor on optics for gravitational wave detectors at the Department of Gravitational Waves and Fundamental Physics. Dr. Steinlechner.
Thank you. Dear candidate, also my congratulations to delivering this nice piece of work. As you know, closest to my heart is ET, the low frequency and low temperature part of ET, and therefore I'm also very interested in the details of ETpathfinder. And I would like to go to chapter 3 here, where you show in figure 3.1 the optical layout of ETpathfinder, which you have also shown us in your presentation. And could you explain a little bit more what the background is of looking here into these two different wavelengths, also into the two different temperature regimes, which you explain a little bit later on. So, yeah, what is the reason, what is the motivation for these two configurations, and also which challenges come with that?
Yes. Dear esteemed opponent, thank you very much for your nice words and the interesting question. I think there is a lot of background. So first of all, let's say we're looking at I think all comes from, if we want to go to cryogenic to reduce the thermal noises, we cannot use fused silica, because fused silica will absorb a lot at cryogenic temperatures. So that motivates for usage of a material that is, in that case, silicon. Silicon with reducing in temperature reduces in absorption as well. So if you use silicon, you need to use a different laser wavelength, and in this case, 1550 nanometer. This is one choice, is the main choice that we can have. It has been proven that it works very well on this technology. So a lot of like optical experiments were done, squeezing and different kind of techniques relevant for interferometry were performed. And there's this secondary candidate, 2090 nanometer. I think it has been shown also that it's very good for gravitational waves detector. It can have lower scattering noises as well. So the background would be to test at two temperatures in which we know that, so for example, 123 Kelvin, I think that's the temperature where silicon, in terms of the coefficient of thermal expansion of silicon, it's almost 0. And then you're reaching that below 20 Kelvin. So you test at these temperatures because you want to test actually if silicon works on that condition with the laser wavelengths. And you can test, of course, ETpathfinder is a bit modular, so you can test at different temperatures at the same time. You can test only one, so as an L behaving detector with heavier masses. So, yeah, I'm not sure if I'm going on the right direction with the...
It's all going the right way, yes.
Sweet.
So, and is there any advantage or disadvantage of the higher over the lower temperature choice?
So clearly the advantage would be to remove the contribution of the thermal noise. So you pretty much all the thermal noise is scaled with temperature. So as you go down in temperature.
Okay. Yes. Let me ask more precisely. So what would the advantage be of the 120 or 123 Kelvin option over the around 15 Kelvin option?
May I ask with respect to thermal noise or in general? Because 123 Kelvin we can reach radiatively. But if you want to really operate in a fast enough time, you really need these conduction heat links or some other way of conducting cooling. And it's already very scary there. If we're looking at that plot that I've shown, actually we can look. Because there it's a low frequency, you're degrading a lot. So this is figure 4.19 at page 114. And we see there that at low frequency, the introduction of the conduction cooling is completely destroying ETpathfinder sensitivity. So for me, just looking at this, the clear disadvantage would be the conduction cooling, that we need to manage that. We need to actively isolating this conduction cooling to reach the temperatures. An advantage for going at 20 Kelvin will be indeed all thermal noises. They go below, so absolutely the entire thermal noise budget there. And for 123 Kelvin, compared to, the big advantage there will be it's easier to reach that temperature. And in terms of technical noises, clearly I think you don't have this low frequency dependency that's strongly coupled. In terms of the coefficient of thermal expansion, so the thermo-optic noise will be, I think, manageable at 123 Kelvin. I think this was, I'm not aware if this was proven, but I think theoretically it's possible. And 123 Kelvin. Yeah, this is what crosses my mind right now. I don't know.
Yeah, thank you. That's answering my question already well. And now you already mentioned, coding thermal noise. So as we see in figure 3.12, this is quite dominating in a certain temperature, in a certain frequency regime. So what can we do, to further reduce coding thermal noise, or what?
Yes. So here, I was simply referring. I was thinking with respect to this, just by looking at equation 3.23, and I think in general for the coating thermal noise there are. So you can simply just looking at this, the loss angles, the loss of the material is very important. So if you make more pure materials, it will help in this case. So we have some candidates on this on figure 3.12 there. For example, amorphous silicon or silicon nitride that they can work in combination with some known materials. Another thing that we can do, you can make the beams a bit larger on the test mass, because I think it's a larger dependency of that. It squares with it behaves with the square of the beam size. So there is actually research with different beam patterns that we can control gravitational waves, because it reduces the thermal noise. So these are some things we can do there, and of course cooling it down. So.
Yeah, so if I remember right, the beam sizes in ETpathfinder are relatively small. What is actually the reason for choosing such small beam sizes if this causes trouble with coding thermal noise?
So initially we have to, if we look at page 58, figure 3.2, there is a buildup of higher order modes as we move the cavities, as we change the radius of curvature. It's a symmetric cavity that has a fundamental mode resonating, but as you modulate the radius curvature, you expect buildup of higher order modes. And you see actually on this plot, the top plot there. So we chose a range that was, we had, I think this can be one candidate. You can choose different things. But this candidate gives you, if you look at the evolution of the bottom plot, on the x-axis you have this candidate, the radius of curvature, with the beam diameter. So these were the typical beam that we chose because, you could guess that if you go on the lower part, it's a bit more unstable in terms of actually choosing a smaller beam size. So I think that was roughly the argumentation there.
So that means that the thought is trying to generate a stable cavity, and we don't mind losing a little bit in coding thermal noise instead initially.
Yeah. So more like, I think, practical reasons than...
Okay, thank you. And that's it on this topic, but I have one more question and would also like to look at one of the propositions, and that's number 7, where you say that future gravitational wave instruments should operate large-scale networks optimized for specific scientific targets. Could you elaborate a little bit on what your thought behind this proposition was and what exactly you mean?
Yeah, so here I was really scared when, so just for the audience, the Einstein telescope will operate in a triangular configuration. That's the baseline right now. And it has actually 6 interferometers. So I was really scared just knowing some stories and some, going to Virgo, like how difficult the actual commissioning is of a gravitational wave interferometer. So if you want to tune a full Einstein telescope with all these degrees of freedom of 6 interferometers, it will be super difficult. And the thought process there was that you need automation between, let's say, vertices or automation between different interferometers. And there has to be a way to make this like local automation for in an interferometer, which is not really achieved right now or at least Virgo, that I was not aware. So if you achieve this local automation of a full interferometer, let's say you're operating with an interferometer, but if you want to operate with Einstein telescope, you should have some coherence between bringing all of them at the operating point. So my thought process there was that we need some automation procedure that makes sure different instruments, different things are checked within different instruments, and we can bring this to the lock state of the entire instrument. So that was the, and of course it links a bit to chapter 5, in which I propose this machine learning approach of the beam patterns.
Okay, thank you, and that's it from my side.
Thank you very much. We continue the opposition with Dr. Danilishin, who is an associate professor of physics at the Department of Gravitational Waves and Fundamental Physics.
Thank you, Mr. Projektor. Dear candidate, first of all, my congratulations with completing this lovely thesis and excelling in such a, as my predecessors commented, such a remarkably broad variety of topics. I would like to ask, to start with asking the question on the introductory chapter. The figure 1.5 or 1.6 really doesn't matter on pages 18 and 19. Could you please explain what is the procedure behind, or what is the meaning of these shaded bands, and what is the procedure, how you get the boundaries of these bands? What is 10% best sources, 50% best sources stand for?
Dear esteemed opponent, thank you very much for your nice words and your question. Yes, so each interferometer has an antenna pattern because we detect gravitational waves. And this antenna pattern is, you can calibrate it, you can select a number of points that are most sensitive to your instrument. So we're looking at Einstein telescope here, but this configuration, ETD, this used to have Einstein telescope 2 detectors, low and high, at 90 degrees opening. So there were 2 L-shaped detectors. And in that case, you can use antenna pattern to calibrate. You can select just based on antenna pattern your 10% best sources. You can assume that for a simple L-shaped, you have the source that comes above with a plus polarization, and that gives you the maximum signal. It's simply a number, a factor of 2 sensitivity. Yeah? So the procedure there was we simulated sources. These sources were randomly in their parameters, so their inclination, their polarization, and their orientation were randomized on the sky. We simulated the sky, and we calibrated the antenna pattern based on that sky. And we simply, after that, we calibrate the curves. So we multiply the curves by these factors that we get as we do the calibration of 10%, 50%, and so on. So what this shows, it shows that the thing that is peculiar here is for Einstein telescope, because the Einstein telescope curve lies a bit above the what's best, let's say the best case scenario for ET. So I'm not sure if that answers roughly how this was produced. Or
I think, except can you specify what was the assumption about the parameters of the sources, such as distance and masses of the components? I guess it was compact binary coalescences that you used here.
Yes. I think that these assumptions, I don't really think I still remember.
No, I do not need the absolute values, but were they also random? Or you assume that they are all the sources distributed randomly on the sky, but still at the same distance from the detector and with the same masses of the components?
So for the first plot, the mass was fixed. And for the second plot, figure 1.6, of course, we were looking at the evolution with masses, so the masses on the x-axis. But the other components, the inclination, the polarization, and position on the sky were fully randomized. The mass calibration, I don't remember exactly which assumption we use for this.
Okay, thank you. You answered my question. So, and my second question would be on chapter 2, because I'm theoretical physicist by training, and I'm always amazed at the Pound-River Hall schema. I'm trying to understand it in vain. So, can you explain the connection between figure 2.3 and the connection and the figure 2.4? So I guess the 2.4 is the, in some way obtained in the procedure that is described on 2.3. So what exactly do you start with in the scheme on 2.3 in order to get the black curve, and under what circumstances you get the blue curve on 2.4?
Yes, interesting question. So figure 2.3 is just a setup of how we typically do the modulation and the achieving Pound-River Hall signals. Yeah. So in that type, you have a laser beam that you modulate. You create sidebands.
Andrei Utina, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await our return in this room for the results of our deliberations.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. I know what's on the line. I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. I know you've won the battle once you've grown. 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
Andrei Utina, the degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Hield is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Please all rise.
Okay. Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Andrei Utina, the degree of doctorate and grant you all the rights attached by custom and by law. As evidence of this, I will now present to you with the degree certificate signed by the rector, the secretary, and the other members of the committee, affixed with the official seal of the university.
Let's first apply this.
Dear Andrei, dear Dr. Utina, very nice to say this for the first time. It's our absolute pleasure to congratulate you on your well-deserved PhD degree here. This is a real achievement, and even more so, considering your studies came with several twists. It was an interesting time. The first one by moving 1 year into your PhD from Glasgow, Scotland to Maastricht, but then having settled in Maastricht, the pandemic hit, which probably affected you more than anyone else in the group. There are many anecdotes one can tell here, but let me pick 2 of the following, okay? Right at the onset of the pandemic, you were at a machine learning workshop related to chapter 5 here on Malta with Rob Vallée and Gideon Kukuk. And there were some statements that the government of Malta intended to lock down the island and not let anyone go out anymore. Well, I guess many people would have loved to, enjoy a lockdown in a sunny island. It's not the worst place to be there, stuck. Our very caring then NICEF program leader, Frank Linde, thought that half a year of hotel bills might be a little bit too much, and he ordered everybody back, onto the next plane to stop the workshop and immediately come home. So actually this happened while officially on the webpage already it said, you're not allowed to go out. You sneaked out and took one of the last planes, and then, had the lockdown in a less sunny place here in Maastricht. Okay. Also, the other anecdote, it's all about Corona, relates to the lockdown, and this is a little further down in time when you were decided to go back to Romania to your family as part, for part of the Dutch lockdown. Then apparently the contract of your apartment ran out, and then you were not here, couldn't take stuff, and then actually 2 other PhDs here, and Viola at Ayatri went to your flat, cleared it all out, put it into bags and so on, and then we're wondering where to put the stuff. And then this stuff actually went to our office, into one of the cupboards, and was sitting there, according to them, for a very, very long time, until you could take possession again. Anyway, so life during your PhD was not always easy, and had for sure some unexpected twists and turns. But now a bit more to the science. But this did not impact on your dedication for science, which we, I think, have all seen here today in your defense. Right from the start through to the end, you tackled your studies with your usual attitude to take things into your own hands, and with loads of energy, push them forward, and persistence to pull them through. This was really a pleasure for us supervisors here to witness, because you always had so many good ideas, and you also had the energy to pursue them, and you tackled them straight on. It was really nice. Your analysis of ETpathfinder noise budget really helped shaping ETpathfinder and resulted in the first ETpathfinder full collaboration scientific paper. I think we will cite this many more times, I think. Also, you did, as we have seen, some of the first experimental work for ETpathfinder with the jellyfish wire prototype setup, and established and fostered with that also a strong and fruitful link between Amsterdam and Maastricht, which at that time was really kind of vital, us coming in as newbies here. A lot of your work happened at the time when when the department was quite small and we were kind of more or less confined to a single office. I'm not sure, some people might still recall, you know, we had an office with 6 desks, Andrei, Viola, Zeb was in there as an intern from Brussels University, Gideon, Sebastian, Jessica. So very nice, fun times. And as a side note to that, we still many of us still fondly remember your regular push-up competitions you had with Zeb and also with Gideon. Really nice. Anyway, so I think it's very important, you know, you were really one of the ETpathfinder pioneers here with the thesis, with these papers, with your work. And by now, our group in Pathfinder has grown significantly, and we look back fondly and appreciate your role as one of the first ones to really get this started. So let me summarize. We really congratulate you wholeheartedly to these achievements and your well-deserved PhD degree. So congratulations to you, your family, your friends on this very special day.
Thank you, Stefan.
Dear Dr. Utina, also on behalf of Maastricht University, I congratulate you with the doctorate degree that you've just required. My congratulations also go to your supervisors, your family, friends, and colleagues. Now, before I close this meeting, I would like to thank all members of the degree committee. Your participation is much appreciated. What's next? After closing this meeting, we will all go to the reception in the refectory elsewhere in this building, where you can all congratulate the new doctor. However, before we do so, we will use the opportunity to take some pictures with the candidate and the full degree committee at the stairs on the other side of this room. Thank you all very much for attending this milestone event for Andrei Utina. I now close this academic meeting.